Assalamu alaikum everyone. Hope you guys are doing great. Today I will discuss about low density parity check or LDPC. So LDPC is basically a linear block coding technique. A linear block coding technique where the message signal is divided into independent blocks. So it is a linear block coding technique where the message signal is divided into independent blocks. That means the message signal is sent or received independently. It has fixed size or length, or it can be variable size or length. So there are two types. It can be fixed size or length, or it can be variable size and length. Okay. Now let us go deep into this topic. By the way, it is a memoryless technique where the codes and blocks are independent. We have already noted that the codes and blocks are independent, so there is no need to store previous blocks. That's why this is memoryless technique. Okay, so no need to store previous blocks here. These are some important theories you must remember, and also it is based on matrix. The encoding and decoding of this technique is based on matrix. We'll get to know about these things. So first of all, let us consider the code word here. Let's consider code word CW. Here code word will be written as N. The data word will be written as K, and the parity block length will be written as M. So here M will be code word minus data word, or N minus K. We have to remember a small thing and a very important thing, which is code rate. It is defined as R, so R equal to K by N, data word by code word. There is a condition here: if R equal to 1, then there will be no redundancy bits. So it results that it will be a error free. It will be error free. Okay. Now let us go through a small scenario here. 7, 4. What does 7 visualizes? 7 is actually the length of code word, or N, and the 4 is the length of data word, which is K. Now previously we have talked about a matrix, that it is based on matrix, so we will get to learn about the matrix now. So matrix has dimensions, row and column. So the dimension of the matrix is depending on the N and K here. So dimension will be K minus 1 into N. That means 4 minus 1, 3 into 7. This will be the dimension of the matrix. Dimension of the matrix. Now what is the name of the matrix? Question can be arised. The name of the matrix is sparse parity check matrix, which can be written as H. So this is very important. H is a sparse parity check matrix. We will need that matrix in every cases, encoding, decoding, both cases. So let us consider an example now. Let us consider the data word is 1, 0, 1, 1. The dimension will be then 3 into 7, the sparse matrix dimension. Now let us visualize the edge for the first time. So the edge is combined with C1, C2, C3, all goes through the C7. So we have to remember a small thing here. The matrix is totally a random matrix. So in your question paper, the matrix will be given. So don't need to worry. So let us take the matrix here: 1 1 0 1 1 0 1 1 0 1 1 1. Now why I am dividing this? Because the matrix is combined with two parts. The first part is data word part, and the remaining part will be the parity part. So that will be the parity part. Now let me write the matrix first, the row and column. Have you noticed the matrix before? Yes, this is identity matrix. This is a special matrix used in the part of the H or sparse matrix. So let us denote C1, C2, C3, C4, C5, C6 and C7. Okay. For our betterment, let us visualize the code word here. Code word 1011. Our 3 parity bits will be given here after the answer. So the next part will be very important. Let us carefully see this. First of all, considering the ones. So let us consider the ones. Consider ones. So let me write first, then I will explain. C1, C2, C3, C4, P1 equal to 0. Now I am deducting C3 from this bit stream. Why I am removing the C3 here? Here comes the process. Now we have to consider these two things: 1011, the data word, and this part for the P1 segment. For getting out the P1 or the first parity bit, we have to consider this first row and this data word. So carefully see these things. 1 into 1, C1 into the first bit. So 1 into 1, it will be 1. So C1 here will write 1. Then C2 is 1 and this part is 0. So 1 into 0, it will be 0. And remember, we have removed the C3. Why? Because here we can see the 0. So it is already 0 here. That's why we have removed the C3 from this bit stream. Then considering the C4, 1 into 1. So it will be 1. Now the P1. So what will be the digit of P1? See, here are even numbers of 1. So if we can we XOR them, basically we have to XOR them, our value or our result should be 0. So in order to get 0, we have to consider here 1 of even numbers of 1. So in order to intake the even numbers of 1, we have to consider P1 as 0. If we consider P1 as 0, so there will be 2 1, that means even number of 1, so the result will be 0. So here we can get P1 equal to 0. First parity bit is got from here. Now let's consider the second parity bit or P2. For the P2, let's see which of C1s we will need to carry. The first one is already, obviously it will be carried. C2, now see C2 we can see 0, so C2 will not be considered here. So C3 will be considered and C4, and finally we will write P2 and equal to 0. Okay, then we have to XOR them. So okay, now let's consider this row and this data word. 1 into 1, 1. 0 into 0, oh, we have already removed the C2. So let's get to the C3. 1 into 3, 1 into 1, so it will be 1. 1 into 1, it will be 1. Okay, now we are seeing here odd numbers of 1. In order to get 0, and we are also doing here XOR operation, we have to somehow maintain the even number of 1. To maintain the even number of 1, we have to include extra 1 here as the parity. Now it is even number, or 4 is even number, so even number of 1 is present here, so the result will be 0. So from here we can write P2 equal to 0, sorry, P2 equal to 1, my bad. P2 equal to 1. Now for the last P3, C1 is already, we should remove C1 because here is 0. You can see C2 will be here, and then C3 will be here, and C4, and we are considering P3. We have to find out the P3. Okay, then the XOR operations will be done and the result will be 0. So C2, we are considering this row, third row, and this data part. So 1 into 0, it will be 0. 1 into 1, it will be 1. 1 into 1, it will be 1. So we are seeing two ones here, so it is even number. That's why it will be 0. So P3 will be 0. So Eureka, we have already find out the parity bits. So the code word will be 1011010. That's the final answer. Now we have finished the encoding part. Now let's go to the decoding part. We are starting the decoding part. So it is our received code word. Our H matrix or the sparse matrix will be needed here, and this matrix this code word, we will just transpose the code word. So if we consider it as a matrix, it is basically one row here and 1 2 3 4 5 6 7 columns here. So if we transpose, let us consider it as S. So ST will be 1 0 1 1 0 1 0. So that will be the transposed form. In order to decode, we have to do this operation H into ST. So let us write the H from the previous. The H was 1 1 1 0 1 1 0 1 1 0 1 1 1, and there will be our identity matrix multiplied by the ST. 1 0 1 1 0 1 0. Okay, so let us simply multiply the matrix. Here we can see 3 into 7 matrix and a 7 into 1 matrix. So it will be a 3 into 1 matrix if we know the multiplication rule of matrix. So first of all, it will be 1, then again 0 0 0 0 and 0. It will be 1 0 1 1 0 1 plus 0 0 0 1 1 triple 0. So all we have to do the XOR operation here. Sorry, I have written the plus. There will be XOR operation, XOR sign. You have to write the XOR sign in your question answer paper. So if we do the XOR operation, the first row, the XOR operation will result to 0. Second, there is 4 ones, so even number of 1 will result to 0. Again 2, it will be 0. So here we can see that there is no 1 here, so it is error free code. So the received code word we have got, it is totally error free, and we can check it through this operation H into ST. If we got every row the answer, if the answer is 0, so it will be called as error free received code or code word. Now question can arise that if something here is 1, that will be not error free, that will be error. So what will be then, or what will do to remove the error or solve it? So let us go to our part 3 of this section or class, which will be remove the errors. So let us consider if received, obviously we receive a noisy code here 1 0 0 1 0 1 0. So let us consider this is our received code word. Now again we have to decode it through H into ST operation. Our H was the same 1 1 0 1 1 0 1 1 0 1 1. Okay, Then our identity matrix 1 0 0 0 1 0 0 0 1. Simply we'll multiply 1 0 0 1 0 1 0. Okay, let us multiply. That will be 1 0 0 0 0 0. Okay, and the second row will be 1 0 0 1 0. Okay, the last row will be 1 0 0 0. Okay, so the result of the first row is 0, but the second row we can see here 3 1. So this is odd number, so the XOR operation result will be 1. And again here you can see 1 1, odd number, so it will be 1. This is our S1, this is our S2, and this is our S3. So we can see there are 2 errors, because we are seeing in our S2 and S3 we have got 1 here, not 0. To check how many errors we have got in C1, C2, C3, C4, each of the data word, we'll use a term called voting. In voting, let us write C1, C2, C3 and C4 first. For C1, it is C1, C2, C3, C4, C5, C6 and C7. Sorry. Okay. So in C1, let us consider the first column and the result. So if we multiply 1 into 0, it will be 0. So it means no error. 1 into 1, that means it will result 1. So 1 error. Then 0 into 1, it will result 0. So finally we are getting C1 1 error. Then for C2, let us consider this column. 1 into 0 0, no error. 0 into 1, no error. 1 into 1, 1 error. Let us consider C3. 0 into 0 0, no error. 1 into 1, 1 error. 1 into 1, 1 error. So 1 plus 1, 2 errors here. Again for the C4 we can see 2 errors. So for each C1, C2, C3, C4 we can see that 1 error, 2 errors and 2 errors. Now at first we will start with the maximum number of errors here. So let us consider C3. It has 2 errors. So in the ST or the received code word, we have to replace the third number bit 1 0 1 2 3, the third number bit with 1, because it is 0 here. So 1 0 replacing 0 with 1, 1 0 1 0. It will be one new received code. It will be a new code word basically. So we have to again perform the h.st operation here. Performing the h.st operation, h will be the same 1 1 0 1 1 0 1 1 0 1 1 1. Then it will be the identity matrix 1 0 0 0 1 0 0 0 1. Let us transpose the S or the received matrix or the replaced matrix. 1 0 1 1 0 1 0. Simply we are now multiplying 1 plus 0 0 0 0. 1 plus 0 plus 1, 1 to 1 1, 1 to 0 0, 1 plus 0 0 1 0 0 0. Okay, if we consider the first row here, the result will be 0. Second row, there are 4 1, so even, so it is 0. 2 even, so it will be 0. Yes, we have got our no error here, because there is all 0 we can see here. So the replaced code word here we can see is the correct code word. Now here we can also find that there can be 1, again there can be 1. So in this case, if we find again 1 in these 3 rows, we have to take again the C4 here. So by taking the C4, we have to replace the 4th bit from the replaced code. So here the 4th bit will be 1011. So 1 will be replaced with 0. Then again it will be go through the process h.st, then it will be 000. But in this scenario or in this example, we have already got the 000 or no error by replacing only 1 bit, which is the 3rd position bit. Sorry, I have to include another term which is Tanner graph. The Tanner graph is basically used to map out each of the code word. Basically it is used, or it gives us a mapping that maps each of the code word. Okay, now let us see the Tanner graph. Here we can see h.st, our operated process here. So let us consider it is as S1, S2 and S3. First of all, we have to write the C1, C2, C3, C4, C5, C6 and C7, and the parity bits. For the parity P1, P2, we have got 3 parity, so P3, 3 parities here. Sorry, my bad, that will be no parity, that will be S1, S2 and S3, or the syndrome. Now for the C1, we are seeing, if we consider the first column and the 3 rows here, C1, S1 and C1, it is 1, so C1 connects to S1 and C1 also connects to S2, but C1 and S3 is not connected because it is 0 here. Then if we consider C2 and S1, yes, they are connected, so C2 and S1. C2 and S2 not connected, C2 and S3, yes, they are connected. If we go to the C3 here, C3 and S1 not connected, C3 and S2 connected, C3 and S3, yes, they are connected. If we go for C4, all of the S1, S2 and S3, 3s are connected, so 3 of them are connected. And for the S5 and S1, they are connected, rest of all not. C6, S1 is not connected, but S2 is connected. And for the C7, S3 is only connected. So this is the Tanner graph. So in the first part we have seen the encoding, in the second part we have seen the decoding, and in the last part we have seen if there can be any noise or error, the errors can be removed. So that's all for the LDPC or low density parity check. Hope you guys like the video. Please do share and support. Thank you so much.